Those of you who know floods will know that floodwaters carry within their murkiness every contaminant soluble in water. Dr. John Pomeroy and his colleagues at the University of Saskatchewan had observed an increase in rainfall on the Canadian prairies. But this is very interesting because you look at the history of the prairies. Some of you are undoubtedly from there if you live here. But what you found historically is most of the summer events were thunderstorms. And you get 2 hours of very heavy rainfall and then the thunderstorm would end. What we're seeing now is that there is more precipitation, but more of that rainfall is being produced by multi-day rainfall events generated by frontal storms coming, for example, from the Gulf of Mexico, as opposed to those shorter-term local thunderstorms. And this represents a change in weather patterns that is actually projected to occur in many parts of Canada. We can expect more precipitation generally in many places, but that precipitation may come in fewer and more powerful storms. And the reason for this is that the atmospheric circulation patterns associated in part with the weakening and meandering of the jet stream are pushing storm tracks northward toward the poles. And what is very important about this on the prairies is that longer, heavier rainfall events dramatically affect water quality. Heavy runoff producing rains wash nutrients, bacteria, and toxic contaminants from agriculture and urban lands into waterways. And Pomeroy and his colleagues have observed a 10,000-fold increase in the mobilization of fecal coliforms in these multi-day events compared to the mobilization occurs during thunderstorms. So in Manitoba and the central Great Plains, increases in the intensity and duration of extreme weather events that appear to be becoming the norm are causing a great deal of contamination loading. And the place where this is most obvious is Lake Winnipeg. And this is a phenomena you may want to note here. This is a serious problem, and this is why the Global Nature Fund recently recognized Lake Winnipeg as Threatened Lake of the Year for 2013. Canada earned this most unfortunate distinction because the judges were of the opinion that the geographical extent and rate of eco-hydroclimatic change that are the cause of 15,000 square kilometer algal blooms in Lake Winnipeg, that these forces, these processes were unparalleled anywhere else in the world. And our fear is that that might actually be true. Now, you're lucky to have avoided earlier on algal problems here, but with rising temperatures, you can't be assured of that. And those who haven't dealt with cyanobacteria, I should point out that one prominent researcher called them the cockroaches of the aquatic world. They're uninvited guests that just won't leave. They're early life forms that have survived ice ages and asteroid strikes, which means they're difficult to get rid of once they're present. And unfortunately, because of warming water temperatures and the increase in nutrients runoff, they like it better and better in Canada all the time. And they also appear to be becoming more toxic as their numbers increase. Spring flooding throughout the Great Plains region has been increasing in the past decade, setting new records. But it's not just Lake Winnipeg that's been affected. Increases in the intensity and duration of precipitation events have begun to increase cyanobacteria producing nutrient and pesticide inputs into rivers and lakes right across Canada. And recent research demonstrates that cyanobacterial toxins have now been detected in 246 water bodies right across Canada. And these toxins produced by blooms are a known danger to humans and to animals. Now, I want to point something out here that is quite significant, because when you look at your lake and you're threatened by eutrophication, that's a serious proposition. But we're not the only ones that have this problem. Freshwater eutrophication has in fact been identified as one of the 10 most worrisome environmental challenges facing humanity today. It's everywhere. And I should point out that Lake Winnipeg's problems just got a whole lot more complicated this fall with the announcement that zebra mussels have finally found their way into the Lake Winnipeg system. This is not something you want to happen here. In fact, as soon as I found this out, I texted Anna Warwick-Sears, And I said, I hope you can redouble your prevention efforts here in the Okanagan. Think of it this way. Your mother has been ill with some sort of immunological condition that doctors are having trouble treating. And now she has fallen and broken her hip. And unfortunately, well, Lake Winnipeg is a big problem. It's not the problem. The problem is much bigger. A combination of ecological, hydrological, and climatic change is altering the character of the interior of the continent. And I have to say that it was with this realization that for us, the lights really went on. And while we may not have perceived it as such, what's happening in the Arctic and in the north is exactly what's happening in much of the rest of Canada. Warming is causing the post-glacial hydrologic wealth of Canada to change form. Now, the water's not disappearing. Water doesn't do that. What's happening is that liquid water is moving to a different place in the hydrosphere where it may not be available for our use when we want it, and where under certain conditions it can also cause a lot of flooding damage. And this is going to add additional edge to the already existing natural variability that Scott showed for this region, but also for regions in much of the rest of Canada. So what these observations confirm was that temperatures are in fact energizing the global hydrologic cycle. And I have to say this is really evident where I live in the main chains of the Rocky Mountains. There's evidence now, and I always find this is quite interesting because I show this because this is Glacier National Park in the United States, where they've lost all but a few glaciers since 1860. And the reason why I show this is that the Americans knew a lot about what was happening to their ice, and therefore it attracted a lot of public attention. Well, we know what's happening to our glaciers now as a result of the work of the Western Canadian Cryospheric Network, and we have evidence now that as many as 300 glaciers disappeared in the Canadian Rockies alone between 1920 and 2005. And the evidence suggests that this loss is accelerating. The same warming that is causing permafrost to thaw in the north, glaciers to disappear in our western mountains, and changes in precipitation patterns on the prairies is also causing water left on the land after the last glaciation in the Great Lakes region to evaporate. Now, this is something I think, given Scott's presentation, it's something you may want to pay close attention to, because there's such a fine balance between temperature and evaporation. And maintaining lake levels is going to be more difficult in the future. And I thought it was very interesting when Scott outlined how much water there was in your system. Well, back of the envelope calculation of the decline of water levels in Lake Huron alone suggests that as much as 67 cubic kilometers of water may have disappeared from that part of the Great Lakes system since 1997. So you're talking about many times the volume of Okanagan Lake. So the question we ask is, where is all this water going? Well, one of the places it's going is into the atmosphere, where it becomes available to fuel more frequent and more intense extreme weather events. And we're seeing this, we tend to look at Canada, but we're seeing this certainly in Canada, but we're seeing it in Europe. The flooding events there in the spring in Central and Eastern Europe caused $22 billion worth of damage. We're also seeing it widely in the Northern Hemisphere. And the algorithm upon which this assertion rests is one of the most basic principles in atmospheric physics. Warmer air simply holds more water, and the amount of water the atmosphere can hold increases by about 7% per degree Celsius, or 4% per degree Fahrenheit. So what's the problem with that? Well, the problem is that our entire built environment, including urban water supply systems and expensive stormwater infrastructure, are all designed for an earlier, more stable climate. A recent report published by the National Academies in the United States in late 2011 confirms how serious the loss of hydrologic stationarity could be in North America and around the world if current trends persist. The report concludes that continuing to assume that the past is a guide to the future is no longer practically or legally defensible. And what this means is that much of the old math and some of the old methods of managing water will not work in the changing circumstances, and there are liability issues associated with this. And these liability issues are already being unmasked. After the 2011 flood, the government of Manitoba spent $1 billion on disaster relief alone. And I should point out coincidentally that this is the exact amount of the government's deficit the following year. But in addition, the government of Manitoba now faces $1.3 billion in lawsuits related to the flood. And from this, we see that there is a direct link between hydrology and economy. As we saw in Manitoba in 2011, and we saw in Alberta this year, uninsured losses can be 8 to 10 times greater than those covered by insurance. But insurance is not the only form of liability that's being affected by these events. And I was just recently at a seminar in Vancouver on this too, and one in the US. What we're seeing is that tort law challenges, there's three types: there's criminal, there's civil, and there's tort law. Tort law challenges in the United States related to claims of personal and property damage due to flooding suggests that it will only be a matter of time before knowingly making land use decisions based on outdated hydrologic mathematics and models could ultimately land municipal managers, engineers, consulting professionals, and even political leaders in court. And that is an interesting prospect because of the need for greater resilience in the face of hydroclimatic change. It will soon perhaps be economically less desirable to design for earlier standards for homes, buildings, and infrastructure. Scientific, I was so pleased to see your title slides here had atmospheric rivers on them. That was really good. Because what we're seeing is scientific attention focused on atmospheric dynamics related to warming has revealed some very interesting phenomena that validate the concerns of the U.S. Academies of Science. And that's this discovery of atmospheric rivers. These corridors of intense winds and moisture can be 400 to 500 kilometers across and thousands of kilometers long. And they can carry the equivalent to 7 to 15 times the daily discharge of the Mississippi River into the Gulf of Mexico. And I just wanted to add a thing on this because you had that up there. Atmospheric rivers have likely existed for an eternity, but only now, because of satellite radar, do we know of their existence and can track them and their effects. And as was pointed out in the picture that was on your screen, and also this one here, perhaps the best known atmospheric rivers are those regularly occurring high precipitation events that pour down upon the west coast of North America. And we call them the Pineapple Express. And the Pineapple Express begins as a narrow stream of wind of hurricane strength. And as it crosses the warm Pacific, the atmospheric river fills with water vapor. And some 42 atmospheric rivers impacted California between 1997 and 2006. And we know that 7 floods in the Russian River in Northern California were all associated with these Pineapple Express conditions. And if you haven't seen this, when an atmospheric river comes ashore, it's like being hit by a fire hose. And a single California atmospheric river storm in 1999 caused 15 deaths and $570 million worth of damage. Now, atmospheric rivers can produce flooding of the magnitude that we saw in Australia and Pakistan in 2010, and possibly in parts of the central Great Plains region of North America in 2011. So you can bet that all of this was very much on our minds when on the evening of Wednesday, June 19th, rain began to fall in the small mountain town of Canmore where I live. Now, many people say that flooding of this magnitude could never have been predicted. Flooding of this magnitude in this region has been predicted since 1979. And this didn't stop politicians from claiming it was a 1 in 1,000 year event, but it wasn't. What's troubling here is that it was a 1 in 60 year event, if that means anything anymore. And according to the Rocky Mountain Outlook, the town of Canmore began observing the rising creek waters at 7 p.m. on the evening of the 19th. Nearly 5 hours before that, University of Saskatchewan hydrologist and climate science John Pomeroy, who I've already mentioned, was in Canmore with a research team. So we were really lucky. We had minute by minute, hour by hour hydrological analyses of the catastrophe. It's very helpful. So he sent at that time an email to a colleague named Kevin Shook, who is in Saskatoon. And he told Shook, who is an expert hydrologic modeler, that there had already been a lot of rain in the past week and rivers were already high. And he also noted that the spring snowmelt was late and the snowpack was above normal for late June. And he told Shook that while the provincial agency responsible for flood prediction in Alberta had issued a high stream flow advisory, it had stopped short of issuing a flood watch. 7 minutes later, Shook responded. In Canmore, he noted, basements start flooding at 240 cubic meters a second, and he concluded his email by saying, "This will be very interesting."